Okay. So we had discussed that till the last class, it is always the outer shell electrons which were responsible in taking part in bond formation, and inner electrons did not take part in any type of bond formation. This is what we have discussed so far till the last class. But there were certain questions which remained unanswered and could not be explained on the basis of the valence bond theory, and that we are going to discuss now, that whatever the limitations that could not be explained on the basis of valence bond theory, like number one, O2 molecule was found to be paramagnetic. I hope we have discussed the term paramagnetic in one of our previous classes, but those who do not remember, let me tell you that paramagnetic substances are those substances which contains at least one unpaired electron in them. They are called paramagnetic. Now, if you go according to the valence bond theory, oxygen is 1s2, 2s2, 2px2, 2py1, 2pz1. This is the electronic configuration of one oxygen atom, and this is the electronic configuration of another oxygen atom. Now, according to the valence bond theory, these two electrons, okay, these two orbitals, 2py and 2pz, containing the unpaired electron will in them will mutually overlap with each other, and once the oxygen molecule is formed, one cannot expect the presence of any unpaired electron in them, because these two electrons will get paired up. If all electrons are paired up in a system, it is said to be diamagnetic in nature. So what I mean to say is, according to the valence bond theory, oxygen molecule is diamagnetic in nature, but in reality, oxygen molecule was found to be paramagnetic, and this could not be explained on the basis of what is called as the valence bond theory, because all electrons are, according to valence bond theory, should be paired up, because one unpaired electron should pair up with one unpaired electron of another oxygen atom. Second thing that could not be explained on the basis of valence bond theory was, it could not explain the existence of molecular ions such as H2 plus. What are molecular ions? Molecular ions are molecules with charge on them, and if you look at the example that I have just now given, H2 plus, you can see that in case of H2 plus, which is combination of one normal hydrogen and one ionic hydrogen. So hydrogen has 1s1 electronic configuration, and H plus does not have any electron in it. So as a whole, how many electrons are there in H2 plus? There is only one electron in it. But according to valence bond theory, it is not possible to form a bond with one electron, and minimum of how many electrons are required to form a bond? Minimum of 2 electrons are required, isn't it?
Yes, sir.
Okay. So according to the valence bond theory, H2 plus should not exist in nature, but to the contrary, it has been found out that H2 plus molecular ion does exist in nature, which could not be explained on the basis of the valence bond theory. So hence, certain questions like that of these two, which I've just now mentioned, could not be explained on the basis of the valence bond theory. And that is why, to have a proper explanation of these unanswered questions, we need to introduce another theory, which is referred to as molecular orbital theory. So what is this molecular orbital theory? Let us try to understand what this theory tells us about molecular orbital theory. In short, we can also call it as MOT. So, in order to understand the concept of molecular orbital theory, there were certain postulates which were given by molecular orbital theory, which considers the, you can say, the electrons to be completely electron waves. And we know that whenever we talk about any wave, it has this type of symbolization where you have crests and troughs. The crests are the upper ones and the crest is the lower one, the troughs are the lower ones. And suppose when we talk about any atom combining with another atom, so according to the molecular orbital theory, the two atoms combine with each other to form a molecule. And unlike the valence bond theory, which considers only the valence shell electrons in the bond formation, the molecular orbital theory says that every electron, whether it is inner shell or whether it is outermost shell electrons, all are equally responsible in formation of a molecule. So it's not confined only to the outermost shell electrons. Every electron, whether it is valence electron or whether it is inner shell electrons, all are responsible. And during the molecule formation, the atomic orbitals combine with each other to form new molecular orbitals. And once the molecular orbitals are formed, the atomic orbitals completely lose their identity because something new is produced and the older ones lose their identity. So that is one important aspect of the molecular orbital theory, according to which whenever atomic orbitals combine, they will give rise to new molecular orbitals, and whatever electrons were there in the atomic orbitals, that will be getting transferred to the new molecular orbitals. Now, in order to understand it in a better way, let me give you a simple example that what exactly is molecular orbital theory. Suppose you want to prepare an omelette, okay? Double omelette. What is double omelette? Double omelette is the omelette which comprises of two eggs in it. Suppose you want to prepare a double omelette. There are two ways of preparing it. You take egg 1, mix it up with egg 2, and then put it on the frying pan. So you will get this type of situation. Okay, so these are the egg whites, and when you mix them up before putting them on the pan, you cannot make out that which particular portion has come from which egg, because it has been mixed up before putting on the frying pan. And this is same as that of molecular orbital theory, which says that when atomic orbitals combine, they completely combine with each other and you cannot make out which electron is coming from which particular atom. as they completely get mixed up. Now, there is another way. You first break one egg, put it on the frying pan, then break another, put it on the frying pan. So here, as you can see, that you can easily mark that which particular portion of the egg belongs to which one. So this is similar to that of valence bond theory. This is valence bond theory, where only the valence shell electrons are common in between the two, and this is molecular orbital theory. This is molecular orbital theory. So once a molecule is formed, you cannot make out the fact that which particular molecule, which particular atom and the electrons that are coming in the bond formation actually has come from which particular atom. So they completely get mixed up. So that is the concept of molecular orbital theory. So hence, we can understand the molecular orbital theory by suggesting that every electron, whether they are inner shell or whether they are outer shell, are ultimately responsible in the bond formation. And it is not only the valence shell electrons that are responsible, but every electron is responsible. So, to understand it in a better way, let us consider an atomic orbital. Let us consider an atomic orbital which is represented by an electron wave like this. And this is another atomic orbital which is also represented by this. So as you can see that the first part of both the atomic orbitals are crest, which means that when this atomic orbital will combine with another, so we use the term called in phase. In phase. What is the meaning of the term in phase? It means that the crest will combine with the crest and the trough will combine with the trough. And if it is so, then the resulting molecular orbital will have greater magnitude. The crest will also increase in size and the trough will also increase in size. Which means that according to molecular orbital theory, the two combining atomic orbitals, if they are in phase, then there will be formation of the bond. It will be favorable for bond formation. And accordingly, if psi A is the wave function of the first atomic orbital and psi B be the wave function of the second atomic orbital, then the resulting molecular orbital will have wave function of psi A plus psi B. It means that they are getting added up. But in atomic structure chapter, we have learned that it is not the psi A or psi B which has physical significance, but it is the square of the psi which has physical significance, which gives us the probability density function. So if you square them up, then the molecular orbital will have this probability density function, which will be psi square A plus psi square B plus twice psi A psi B. So here you notice one thing, that the electron density of the atomic orbital A was psi square A. The electron density of atomic orbital B was psi square B, but when they are in phase and they form bond, there is an extra increase in the electron density by the factor twice psi A psi B. So hence we say that when the two atomic orbitals are in phase, the electron density between the two atoms increases by the factor twice psi A psi B. And whenever electron density increases in between the two nuclei, so this particular you can say molecular orbital whatsoever is produced is favorable for bond formation, and such type of molecular orbital which is formed as a result of in-phase combination is referred to as bonding molecular orbital. Bonding molecular orbital. So in order to be in phase, it is important that the crest should overlap with crest and the trough should overlap with trough. Then the resulting molecular orbital will have increased electron density by the factor twice psi A psi B. Is it clear?
Yes, sir.
Now, what is the second possibility? If they are out of phase. So when they are out of phase, then let us say that the second atomic orbital has this type of orientation. It has this type of orientation. This is minus, plus, minus, plus, minus, plus. So here, as we can see, that if this is the second molecular atomic orbital, so this atomic orbital, when combines with this atomic orbital, they are out of phase. Now, what is the meaning of the term out of phase? The plus is combining with minus. And when plus combines with minus, will the electron density increase in between the two or decreases in between the two? One will try to nullify the other, isn't it?
Yes, sir.
So when you are going against each other, so you are not going to enhance each other, rather you try to decrease each other. And this particular wave function will be psi A minus of psi B. And the electron density decreases by the same factor twice psi A psi B. So whereas when it was bonding molecular orbital, the electron density was increasing between the two atomic orbitals, but when it is anti-bonding, it is decreasing between the two atomic orbitals, and this is referred to as anti-bonding molecular orbital. Anti-bonding molecular orbital, which is not favorable for bond formation. See, I give you a very simple example. Sometimes we are in mood, we are at good mood, and if person wants something when we are in good mood, then we can help that particular person. But at the same time, if our mood is not good and someone approaches for help, so it is the same person who is going to say no. And that is why, just like our mood controls us, whether we are going to help others or not, so exactly in the similar way, how the two atomic orbitals are combining with each other completely depends upon whether they are in phase or whether they are out of phase. So if they are in phase, so we can say that a bonding molecular orbital will be formed, and when they are out of phase, an anti-bonding molecular orbital will be formed. So whereas bonding molecular orbital is favorable for bond formation, anti-bonding molecular orbital is not favorable for bond formation. But both types of molecular orbitals are formed simultaneously, and whenever two atomic orbitals combine with each other, they are going to form one bonding molecular orbital and the other anti-bonding molecular orbital. So thus we can say that whenever two atomic orbitals combine, when atomic orbitals combine, say it is atomic orbital 1 combining with atomic orbital 2, so it is going to form simultaneously two types of molecular orbitals, one with lower energy and greater stability, which is called bonding molecular orbital, and the other with higher energy and lesser stability, called anti-bonding molecular orbital. So both molecular orbitals will be formed, one bonding and the other anti-bonding. But out of the two, the one with lower energy is bonding molecular orbital, and lower energy means greater stability. And that is why we can say that during the bond formation, if electrons go to the bonding molecular orbital, so that will be more favorable for bonding. And if the electrons are going to the anti-bonding molecular orbital, so that will not be favorable for bond formation. Understood or not?
Yes, sir.
Okay. Now let us apply this concept of bonding and anti-bonding molecular orbitals individually to all the atoms. Individually to all the atoms, so as to understand that how these molecular orbitals are formed. Let us say 1s atomic orbital of one atom combines with 1s atomic orbital of another atom. So if they are in phase, so I put plus for both of them. And if they are out of phase, then one I will be putting plus and the other I will be putting minus. Now, out of the two, which one is in phase and which one is out of phase? Tell me.
First one is in phase.
First one is in phase because both of them I have shown by plus, means crest combines with crest, and here the crest combines with trough. So in the first one, there will be increase in the electron density between the nuclei of the two atoms. And we know that whenever s orbitals combine with each other, they form sigma bonds. So this molecular orbital called bonding molecular orbital will be denoted by sigma 1s. But if they are out of phase, there will be decrease in the electron density between the two atomic orbitals. There will be decrease, and this will be referred to as sigma star 1s. Whereas the bonding molecular orbital is sigma 1s, the anti-bonding molecular orbital is denoted by sigma star 1s. Whenever we put star, it means it's not favorable for bond formation. And whenever we have no star, no asterisk sign, so it is favorable for bond formation. Likewise, when we have 2s with 2s, 2s belongs to one particular atom, this 2s belongs to another particular atom. So S is also spherical, whether it is 1s or 2s, both are spherical. So they will also form same bonding and anti-bonding. So there is no difference, but still I am drawing just to understand that only the size will differ, but otherwise, so 2s will also combine with 2s to form sigma 2s and sigma star 2s. Okay?
Yes, sir.
No, sir.
Okay, right.
Sir, in the second one, there would be any line between the two
Same,
triangles.
exactly same. This is called node. Node is the region where the probability of finding the electron is 0. So in both cases, everything is same, only the shape will differ. 2s is slightly larger than that of 1s, but just like the first one, the shape remains the same.
Okay, sir.
By what factor, tell me, the electron density increases or decreases in bonding molecular orbital and anti-bonding molecular orbital? By how much there is a decrease?
2 psi 1 psi 2.
So it will be twice of psi A psi B. So now we move on to, after 2s comes 2p, but 2p are of 3 types, and we know that out of the 3 types of 2p, one of them is involved in sigma bond formation and rest 2 are involved in pi bond formation. So who conventionally we take it as sigma bond formation? 2pz with 2pz. So in general, Z is considered as the internuclear axis, and if it is 2pz with minus plus and plus minus, and when they approach near each other, will they be in phase or will they be out of phase? Tell me.
Out of phase.
In phase.
In phase.
The plus will overlap with that of plus and there will be in phase, and the in between region will increase in size, and this is called sigma 2pz because the type of bonding will still be sigma. But if the pz orbitals are of this nature, then what will happen? They will be out of phase because the direction of approach is this, and in such case the electron density will decrease in between, and again a node will be formed. I'm not drawing the line, so it is sigma star 2pz. So whenever we are drawing star or anti-bonding, you will notice that electron density is decreasing in between, and whenever we are drawing the bonding molecular orbitals, the electron density will increase in between. What type of bonds are formed by px with px and py with py?
Pi bonds.
Pi bonds, which means that they need to be parallel. So let us draw 2px with 2px or 2py with 2py. Because only the direction will be different, but otherwise energies will be same. So one more important thing, according to molecular orbital theory, when the two atoms combine, the atomic orbitals which have same energy and same orientation can only overlap with each other. It means you cannot expect 2s combining with 1s or 2s combining with any of the 2p or 2px combining with 2pz, because two things must be same. Energies should be same, and secondly, orientations, the direction in space must be same. Then only the two atomic orbitals can combine. So accordingly, if it is say 2px, it is plus minus, this is plus minus. So what do you think when they approach near each other? Will they be in phase or out of phase?
In phase.
Phase.
In phase. But because it's a pi bond, the overlapping will be taking place above and below the internuclear axis. So therefore, you will see that as the overlap is above the axis and below the axis, the increase in the electron density is likewise. And this is called pi to px if the combining p orbitals are px, or pi to py if the combining orbitals are py. But they have same energy, whether it is pi to px or whether they are pi to py, because px and py are degenerate, and not only they are degenerate or having equal energy, they are both forming pi bonds as well. And relatively, pi bonds are less stable with respect to sigma bonds. But if the same p orbitals are out of phase. And when they approach near each other, the electron density will decrease in between. And again, there will be node formation, and this will be pi star 2px or pi star 2py, depending upon whether they are px orbitals which are involved or py orbitals which are involved. So what I mean to say, with the help of this particular concept, which is under molecular orbital theory, that whenever two atomic orbitals combine, they always do so to form two types of molecular orbitals, one of which is bonding molecular orbital and the other is called the anti-bonding molecular orbital. After completing, tell me so that I can proceed further.
Done, sir.
Done?
Yes, sir.
Every one of you have done?
Yes, sir.
Okay. So let us now try to write down the main features of MOT. You can understand the things that we'll be discussing now. Main features of molecular orbital theory. Point number one, molecular orbitals are obtained when atomic orbitals of comparable energies and proper symmetry combine together. So energies must be same and symmetry or orientation should also be same. Px cannot combine with Py or Pz. Likewise, S cannot combine with P. While an electron in an atom is under the influence of one nucleus, the electron in a molecule is under the influence of more than one nucleus. So when we talk about an atom has a single nucleus. So when before combination, it was an atom, whatever electrons were there in the atom was under the influence of a single nucleus. But after it combines with another atom, the electrons will now be under the influence of more than one nucleus. If it is diatomic, the electrons will be under the influence of two nucleus. If it is triatomic, 3 nuclei, and that way. This is the meaning of the second point. The number of molecular orbitals formed are always equal to the number of combining atomic orbitals. The number of molecular orbitals formed are always equal to the number of combining atomic orbitals. So we have already learned that if 1s combines with 1s, it will give rise to sigma 1s and sigma star 1s. When 2s combines with 2s, sigma 2s, sigma star 2s. When 2p, z will combine with 2pz, sigma 2pz, sigma star 2pz. When 2py combines with 2py, it gives rise to pi 2py and pi star 2py. When 2px combines with 2px, it gives us pi 2px and pi star 2px. So hence we see that every case, when the two atomic orbitals are combining with each other, they are producing that many molecular orbitals. So two atomic orbitals will combine to give two molecular orbitals, one bonding and the other anti-bonding. Can I rub the second point? Point number 4. The two types of molecular orbitals formed are bonding molecular orbital and anti-bonding molecular orbital. Whereas the bonding molecular orbital has lower energy, anti-bonding molecular orbital has higher energy, than the combining atomic orbitals. So bonding molecular orbital is more stable but has lesser energy because energy and stability are inversely proportional to each other. Are you understanding the points that you are writing?
Yes, sir.
Yes, sir.
Point number 5. Just like atomic orbitals the molecular orbitals also follow Aufbau principle, Hund's rule, and Pauli's principle while filling up the electrons. While filling up the electrons. So what was Aufbau's principle? The Aufbau's principle says that whenever you are filling up the electrons, you must follow the energy. The one with lower energy must be filled up first, followed by the one with higher energy. What was Hund's rule? It says that if the atomic orbitals have same energies, then you have to singly fill them up, and thereafter only the pairing will be possible. And what is Pauli's exclusion principle? The Pauli's principle says that maximum of 2 electrons, that too with opposite spins, can be accommodated in an orbital. So whatever we have learned in atomic orbital, while filling up the electrons in the newly formed molecular orbitals, you need to follow all these rules. And the things will be more clear when we get into the particular examples. When examples will be provided to you, then the things will be much more easier and clear to you. Tell me after you have completed.
Sir,
Yes.
sir, before starting the fourth point, sir, you were explaining a point. At that time, the video got stuck, sir. I couldn't go through that.
What was the point?
Sir, something about the orbitals you were saying is after writing 2px plus 2px, that gives, sir, that point after that you were explaining something.
These two.
Yes, sir. Yes, sir.
That means I told you that whenever 2 atomic orbitals combine with each other, they will produce 2 molecular orbitals, which means that the number of molecular orbitals produced will always be equal to the number of atomic orbitals that will be combining. So 2 atomic orbitals will combine to give 2 molecular orbitals, one with lower energy called bonding molecular orbital and the other with higher energy called anti-bonding molecular orbital. Okay.
Okay, sir. Okay, sir. Thank you.
So after learning or writing down these various points under molecular orbital theory, let us now try to understand and apply the molecular orbital theory in terms of some molecules as well as molecular ions. So to start away with, we'll first talk about hydrogen molecule, which is a combination of 2 hydrogen atoms, as we know, and each hydrogen is 1s1, 1s1, which means that during the formation of hydrogen molecule, 2 hydrogen atoms will combine, and we are going to show it with the help of this diagram. This is say 1s1 of one hydrogen atom. This is 1s1 of another hydrogen atom. So when they combine in phase, they will produce sigma 1s, and if they combine out of phase, they will be producing sigma star 1s. Is it clear?
Yes, sir.
So sigma 1s is the bonding molecular orbital. Sigma star 1s is the anti-bonding molecular orbital. Now each hydrogen atom has 1 electron in the atomic level. Now, when we count the total number of electrons in the whole system, how many electrons are there combining the electrons of both the atoms?
2.
2. So we are considering the energy from lower to upper part. And every molecular orbital which has been drawn in between are going to accept the electrons taken from the atom, because once atom combine with each other, they will completely lose their identity, and these electrons will be transferred to the molecular orbitals in increasing order of energy. So sigma 1s is going to take away both the electrons, and thus this is the molecular orbital diagram of hydrogen. Just see whether you have understood this point or not. Total of how many electrons in the system? 2. So we need to fill them up in order of increasing energy. Every molecular orbital can accommodate maximum of 2 electrons. But in the whole system, because there are 2 electrons, so both of them will go to the sigma 1s. Nothing will go to sigma star 1s. Understood?
Yes, sir.
Now, after filling up of electrons, we need to calculate certain things for each and every molecule, which further helps us to understand the nature of the system. The first thing is bond order, which we have defined as the number of bonds present between the 2 atoms. So according to molecular orbital theory, bond order is calculated using the formula half of number of bonding electrons minus number of anti-bonding electrons. Now tell me, how many bonding electrons are there? Forget about the atomic orbitals now. Count on only this. How many electrons are there in bonding molecular orbital? 2.
2.
And how many are there in anti-bonding?
0.
0.
0. So will not be 1.
Yes, sir.
Which means that bond order of hydrogen in hydrogen molecule is 1. H is singly bonded with another H. Next, we are going to discuss the molecular electronic configuration. We all are familiar with atomic electronic configuration that we have been discussing from chapter 2 onwards, 1s2, 2s2, 2p6. But here it's the molecular electronic configuration. It means that we have to count on only the middle ones, not the corner ones. And we have to start it from the lower to higher. So in sigma 1s, you have 2 electrons. So I write sigma 1s2. And furthermore, I need not write anything because no more electrons are there. And sigma star 1s does not have any electrons. So no point of writing it. Finally, we are going to calculate the magnetic nature. So magnetic nature can be counted on the basis of number of unpaired electrons in the molecular orbital. So as we can see that in molecular orbitals, forget about atomic orbitals, again and again I'm repeating, both the electrons are paired up. So there are no unpaired electrons in molecular orbital, so it will be called as diamagnetic. Any question up to this much, please ask. Is it understood?
Yes, sir.
Everyone, is it clear?
Yes, sir.
Yes, sir.
Okay. Now come to the controversial part that could not be explained on the basis of valence bond theory, and that is molecular ion H2 plus. Yes.
So can you please explain this diagram? I got disconnected.
The diagram is when 1s combines with 1s, it is going to combine in 2 different ways. If they are in phase, they will be producing bonding molecular orbital having lower energy. And if they're out of phase, they will form anti-bonding molecular orbital with higher energy, isn't it?
Yes, sir.
Now, both the atomic orbitals of hydrogen had 1 electron each. So total of how many electrons are there in the whole system?
So 2.
2. So both the electrons will go to the bonding first. And if more than 2 electrons would have been present, I would have given them in the upper one. Understood?
Yes, sir.
Okay. What else? Have you understood the bond order? How to calculate it?
Yes, sir.
Okay. Let us move on to H2 plus. So H2 plus is a molecular ion whose existence could not be explained on the basis of the valence bond theory. And this can be explained on the basis of molecular orbital theory. So H2 plus comprises of one normal hydrogen and one H plus. And H plus doesn't have any electrons. So in the whole system, how many electrons are there?
1.
Only one. And that electron will go to bonding molecular orbital, isn't it?
Yes, sir.
So accordingly, the bond order will be half of 1 minus 0, which is 0.5. Now, molecular orbital theory says that as long as bond order is not 0, that molecule or ion will exist. And we know that 0.5 is greater than 0. So it will exist in nature. Molecular electronic configuration will be sigma 1s1. And what will be the magnetic nature? It has an unpaired electron.
Paramagnetic.
So it is paramagnetic. Clear?
Yes, sir.
Is it understood to everyone?
Yes, sir.
Aditya?
Yes, sir.
Okay. Can I proceed to the next?
Yes, sir.
Yes, sir.
Okay. So let us see now on the basis of molecular orbital theory why helium molecule does not exist. This will be number 3. He2. Helium plus helium. Electronic configuration of helium is 1s2, 1s2. So both have 2 electrons each. So total of how many electrons are there in the system?
4.
4. How you are going to distribute the 4 electrons in order of increasing energy? It will be
2 for bonding
1,
and 2 for
2,
anti-bonding.
3, 4. Okay? Understood?
Yes, sir.
What will be the bond order? Half of 2 minus 2, 0, isn't it?
Yes, sir.
So if the bond order comes out to be 0, it means that such molecules are not going to exist. And because such molecules do not exist, no point in calculating the electronic configuration and magnetic nature. Only for those whose bond order exceeds 0, you are supposed to calculate the bond order for them. Clear?
Yes, sir.
Yes, sir.
Okay. So up to helium, the electronic configuration is ending up with 1s, and therefore we were taking the help of this particular diagram. After helium comes lithium, whose atomic number is 3. So let us see lithium plus lithium. 1s2, 2s1, 1s2, 2s1, which means that this is not sufficient for lithium, as 2s also participates in bond formation. So for lithium, we have to include 1s also and 2s also. So for 1s, as usual, we have bonding sigma 1s, we have anti-bonding sigma star 1s. Likewise, for 2s also, we have bonding sigma 2s and we have anti-bonding sigma star 2s. Here,
Yes, sir.
Sir.
now for each lithium atom, it is 1s2, 2s1, 1s2, 2s1. Now 2 plus 2 is equal to 4. So 1, 2, 3, 4. 1 plus 1 is equal to 2, both of which will go to sigma 2s. Understood?
Yes,
Yes,
sir.
sir.
Now let us calculate the bond order for lithium molecule. Which is half of number of bonding electrons. How many bonding electrons you can see?
4.
4. The lower ones are bonding. And how many are anti-bonding?
2.
2.
Sigma star 1s is 2. So will lithium molecule exist?
Yes.
Yes, sir.
Its bond order is 1. As it is greater than 0, it will exist. Electronic configuration. Starting from 1s, it has 2 electrons. Sigma star 1s, it has 2 electrons. Sigma 2s, it has 2 electrons. Yeah.
Yes, sir.
So from bottom to top, you have to count. So sigma 1s has 2 electrons. Sigma star 1s has 2 electrons. Sigma 2s has 2 electrons. And magnetic nature, what do you think will be the magnetic
Diamagnetic.
nature?
Diamagnetic.
All electrons in the molecular orbital are paired up. It is diamagnetic. Understood?
Yes,
Yes,
sir.
sir.
Any doubt up to this much? Anyone? Please tell me. Fahim, is it clear?
Yes, sir.
Can I proceed further to the next?
Yes, sir.
Okay. Now, till the 2s orbitals, there is no problem because 2s has got only one orbital under it and they are going to form only sigma 2s and sigma star 2s. But the problem comes, or complications come rather, for 2p onwards. Now you have to remember that 2p starts from boron onwards up to beryllium. There is no 2p. It ends up with 2s. So I'm going to categorize boron, carbon, and nitrogen molecule into one type. And the higher ones, oxygen, fluorine, and neon, as the other type. Because they have difference in their energy diagram, and we will have to find out that what is the difference. You know that 2p are 3 in number, 2px, 2py, 2pz. And out of 2px, 2py, 2pz, pz forms sigma and the rest to form pi. So we are going to subdivide the bonding molecular orbitals into two types. And likewise, anti-bonding also into two types. So for boron, carbon, nitrogen, remember the pi orbitals have lower energy. Pi 2px, pi 2py. And the sigma 2pz has higher energy, which is an abnormal result because sigma is more stable as it is stronger bond, and being more stable, sigma should be smaller in energy as compared to pi. But it has been found that the sigma 2pz has higher energy with respect to pi 2px and pi 2py for boron, carbon, nitrogen because of the fact that boron, carbon, nitrogen have very less energy difference between the 2s and 2p energy levels. So due to this very less energy difference, there is repulsion, and this increases the energy of the sigma 2pz. And who is repelling whom? The 2s orbitals, molecular orbitals will repel the sigma 2pz. So it was supposed to be down, and these two were supposed to be at the top. But due to repulsion, it has been found that sigma 2pz is at higher energy level. Rest, these are anti-bonding, pi star 2px, pi star 2py. And this is sigma star 2pz. So simply remember, this is the pattern for 2p. I have not drawn 1s and 2s, but when individually asked, you need to draw 1s and 2s as well. But just I want to focus on the difference. But oxygen, fluorine, and neon follow the normal trend because they don't have small energy difference, and whatever is expected, you get the same. Sigma 2pz has lower energy. Pi star 2px, pi 2px, pi 2py, followed by pi star 2px, pi star 2py. And this one is sigma star 2pz. So you get the difference mainly in these two. Here it is 2 followed by 1. Here it is 1 followed by 2. Are you getting the difference?
Yes, sir.
Yes, sir.
That is the only difference. And I'm not able to put the electrons because I have generalized the thing. But individually, when you discuss their molecular orbital diagrams, you will be able to know. Now, this is the point where the student get confused and they are not able to recollect that what is what. So I give you a very simple and funny way of remembering that oxygen and onwards. This is oxygen. These are eyes of oxygen. There will be two teeth in front of each other. So just consider this to be the inside of the mouth. So 2 and 2 in front of each other. Understood?
Yes, sir.
And the lower ones are juniors. So break one teeth. And therefore it is 2 and 1 in front of each other. Clear?
Yes, sir.
Yes, sir.
So senior ones have two teeth in front of each other. Senior counts from oxygen onwards. And junior ones have 2 and 1. And if you are putting 1 here, it will be 2. If you are putting 2 here, it will be 1. The upper portion is same. There is no difference. Understood?
Okay, sir.
Yes, sir.
And depending upon how many electrons are originally present in the atomic orbitals, so that way you need to fill up the electrons. Can I proceed?
Yes, sir.
Yes, sir.
Okay. So one from the boron family and one from the oxygen family, the most common questions that are asked is draw the molecular orbital diagram for nitrogen and oxygen. Also calculate the bond order and magnetic nature. So one I'll pick from the smaller family, nitrogen, and the other I'm going to pick it from the higher family, oxygen. At first, let me draw the molecular orbital diagram for nitrogen. Nitrogen is N plus N. 1s2, 2s2, 2px1, 2py1, 2pz1. Same way, 1s2, 2s2, 2px1, 2py1, 2pz1. First, we will write their atomic electronic configurations. Now, all are involved, so you have to start from 1s, 2s, and 2p. Put more space for 2p. So this is 1s. This is 2s. And this is 2p. So for nitrogen, remember what did I say? 2, 1, 2, 1. Okay.
Yes, sir.
Now, don't forget to name each and every molecular orbital. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, and this is sigma star 2pz. So first we name each and every molecular orbital. There are 3 boxes here. Now I'm putting in the electron according to the configuration. For each nitrogen, it is 1s2, 2s2, 2px1, 2py1, 2pz1. 1s2, 2s2, 2px1, 2py1, 2pz1. The lower ones, no problem. 1, 2, 3, 4, 1, 2, 3, 4. Come to the 2p. How many electrons do you find as a whole under 2p's?
6.
3.
6. 3 plus 3, 6, isn't it?
Yes, sir.
So 6
No,
electrons
sir.
are to be filled up. And remember, while filling up, you have to follow all the rules. Aufbau's rule, Hund's rule, and Pauli's principle. So how you are going to fill the 6 electrons? These two have same energy or not?
Yes, sir.
Yes, sir.
So put 1 electron each. 1, 2, then 3, 4. Clear?
Yes, sir.
Yes, sir.
5 and 6. Is it understood? How have I filled them? 1, 2, 3, 4, 5, 6. Yatke besi hole 7, 8, 9, 10, 11, 12.
Sir.
Okay, now calculate the bond order. Half of what minus what?
10 minus 6, 10 minus 4.
Bonding are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Anti-bonding 1, 2, 3, 4. There are no anti-bonding in 2p. So it will come out to be 3. So nitrogen is triply bonded with another nitrogen. So bond order is 3. Clear?
Yes, sir.
Yes, sir.
Electronic configuration. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Now, pi 2px and pi 2py have equal energies. And if they have equal energies, they should be written one above another, both of which contain 2 electrons each. Clear?
Yes, sir.
Yes, sir.
And then sigma 2pz. What about magnetic nature?
Mm,
Paramagnetic.
Diamagnetic.
Do you find any unpaired electron in the molecular orbitals? Forget
No,
about
sir.
No, sir.
atomic orbitals, only molecular orbitals. So all
No, sir.
are paired up. Understood?
Yes, sir.
So don't look at the atomic orbitals. They have completely lost their identity once molecules are produced. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, all are paired up. So it is diamagnetic. Okay.
Yes, sir.
Now, because this time objective questions will be asked, so you can expect various types of questions, but no matter, whatever be the pattern of question asked, if you are familiar with the basics, then you can answer any question. Let us try out for oxygen molecule. The valence bond theory would not explain its paramagnetic behavior, but molecular orbital theory has done this. Let us see how it has done. The oxygen molecule is O plus O, 1s2, 2s2, 2px2, 2py1, 2pz1. This is also 1s2, 2s2, 2px2, 2py1, 2pz1. Atomic number is 8. So we cannot follow the same diagram for oxygen, isn't it?
Yes, sir. Different.
Yes, sir.
So we have to make change in the 2p. 1s and 2s is same. There is no problem in that. But we have to make changes in 2p because I told you that oxygen belongs to the senior level. So they have 2 teeth in front of each other. So this will be the energy diagram, molecular orbital diagram for oxygen molecule. And it is 2p4, 2p4. sigma to pz, pi to px, pi to py, pi star to px, pi star to py, and sigma star to pz. So total of how many electrons are there in 2p?
8.
8.
8. So you need to fill it up in a systematic way. Let us see how 8 electrons are to be filled up here. 1, 2, 3, 4, 5, 6, 7, and 8. Understood?
Yes, sir.
Yes, sir.
Okay. Now calculate the bond order. Write the electronic configuration. First, you write down the electronic configuration. It will be easier to calculate bond order. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, pi star 2px2, pi star 2py2. So bond order can be calculated without looking at the diagram. You can look at the electronic configuration. Asterisk নথকা গোটেইকেইটা বন্ডিং কিমানটা ইলেক্ট্ৰন আছে বন্ডিং অন ও এটো 2px pi star 2px1 আৰু 1 হ'ব নহয়
Oh, sir.
Oh, sir.
they have 1 in electron, it will not be 2. So pi star নথকা কিমানটা ইলেক্ট্ৰন আছে 1 2 3
10.
4 5 6 7 8. We are missing out something.
No, sir.
We are missing out
Sigma 2z.
sigma 2pz2 we are missing. Just after this we have this. So there will be 10 electrons. Okay. And how many are anti-bonding? 1 2 3 4 5 and 6. So it will come out to be 2, isn't it?
Yes, sir.
Oh, sir.
Now is it diamagnetic or paramagnetic?
Paramagnetic.
Paramagnetic.
Yes. Magnetic nature is paramagnetic. Where are the two unpaired electrons present in oxygen molecule?
Pi star 2px or pi star 2py.
Yes. In pi star 2px and pi star 2py, we have two unpaired electrons, and therefore oxygen molecule is paramagnetic. So for the first time, the confusion over why O2 molecule is paramagnetic could be sorted out on the basis of molecular orbital theory. So both the points that could not be explained by valence bond theory, that why H2 plus exists or why O2 molecule is paramagnetic, could be sorted out by molecular orbital theory. Understood?
Yes, sir.
Yes, sir.
So this much is required under your molecular orbital theory. So see, if I directly start away with drawing the diagrams, you will not understand anything. So where from these diagrams have come, to understand it, we have to take the help of linear combination of atomic orbitals, where we discussed that when two atomic orbitals combine, they can do so in two different ways, if they are in phase and if they are out of phase. So all the lower ones are resultant of in phase, which are called bonding molecular orbital, and all the higher ones are resultant of out of phase, which are anti-bonding molecular orbital. Every molecular orbital will have a different shape, but irrespective of whatever be their shapes, we represent each and every molecular orbital with box only when we draw the molecular orbital diagrams. Just as when we used to draw the atomic orbital diagrams, we used to represent them as box, but in reality some were spherical, some were dumbbell, but irrespective of whatever shapes they had, we were representing them all with the help of boxes. So likewise, in molecular orbital theory also, every molecular orbital will have a different diagram, which we discussed under in phase, out of phase, in phase, out of phase. But ultimately, all are supposed to be represented by box only. And whatever electrons were present in the combining atomic orbitals will be transferred to the molecular orbitals. Understood?
Oh, sir.
Yes, sir.
So this much you practice, at least the molecular orbital diagrams. Some molecules we did not discuss because if you understand these, you can also carry out the calculations for other, but at home you can try out for beryllium molecule, carbon molecule, and fluorine molecule at home. Clear?
Okay, sir.
So beryllium, you have to show it does not exist. And how you can show that it does not exist?
Bond order is 0.
Yeah, its bond order will be 0. Both of them will exist. You will get carbon's bond order to be 2 and fluorine's bond order to be 1. So just check it. And carbon and fluorine's diagram will be different. Carbon belongs to the category of nitrogen and fluorine belongs to the category of oxygen. So whatever diagram we had drawn for nitrogen, same will be the diagram for carbon. And whatever we have drawn for oxygen, same will be the diagram. Diagram means only this difference will be there for fluorine. Okay.
Yes, sir.
Yes, sir.
Great. So thank you. I end up here. So next class,
Thank you, sir.
we'll discuss some advanced level questions on molecular orbital theory. To prepare Korea. Bye bye. Good night.
Thank you, sir.
Thank you, sir.
Thank you, sir.